In this video, what I want to do is show you Marlowe in full. I'll explain the data types that build up Marlowe, the different constructs that we have, and some of the other aspects of the language. So in a nutshell, what we have in Marlowe is an embedded domain-specific language. So Marlowe is embedded in Haskell as a simple Haskell data type. We've modeled its semantics step by step as a contract evolves, as in Haskell itself, and we can use that on the blockchain using Plutus, but we can use the same semantics to understand how contracts behave by simulating them in the Marlowe playground, which we'll talk about a bit later on. It runs on a UTXO blockchain, but one that has a slight extension in that data can be transmitted when at a spending of a UTXO. Not only does an asset get transferred, but also we are able to transmit some data at that point, and that is enough for us to ensure that the contract persists on the it's passed as data between transactions effectively. Now, in fact, we model Marlowe as a single Plutus program. The Plutus program is what's called an interpreter for Marlowe. It's the thing that runs Marlowe programs. So we have in terms of trustworthiness, we have a single program, which is, you can check, is open source, which runs the contracts on the blockchain. So we feel that's better than writing a compiler which would translate each contract into a different Plutus contract. It might be harder to see that is doing what it should do precisely. We do analysis of Marlowe programs using the SMT solver Z3. We'll talk about that in a later video, as we will talk a bit about how we've done formal machine-checked proofs using Isabelle. And finally, we've got the Marlowe playground, where we can develop, analyze and simulate Marlowe programs. So that is an overview of the whole Marlowe proposition, if you like. But what I want to do in this video is talk about the data type, the contract data type, which is what Marlowe is. There are 5 different kinds of contract. There's a close contract, there's a payment, there's a conditional. Depending on a particular observation, one of 2 contracts is performed. There is a when construct, which waits for actions to happen, and a when can wait for a number of different actions. And when the first of those to happen happens, a particular contract is triggered. But when is the contract that also has a timeout. So the timeout is there to ensure if none of the actions happens, the contract will continue as the alternative, as the timeout contract. And we're also allowed to give a name to values in contracts using a let. Okay, so let's just talk through those in a bit more detail. The close construct closes a contract and refunds any money left to account owners. Inside a Marlowe contract, there are local accounts that belong to the participants in the contract, and if an account belongs to Alice and some money is left in that account, it will be returned to Alice when the contract is closed. We can make a payment. Now, payments are made from accounts to payees, and we specify the value to be paid. And then the final part of the pay construct is the continuation, how the contract carries on after the payment has been made. So there we've got a payment being made, and we've got the conditional here. We have, if the condition is true, we do one contract, cont T. If it's not true, we do cont F. So that allows us, based on conditions, the contract can evolve in one way or another. And the when contract has these three components. It has a set of cases It has a timeout value, and it has a contract that we perform if that timeout is reached. And each case consists of an action and the contract that is triggered if that action happens. So before the timeout, when one of the action happens, the corresponding contract is performed. On the other hand, when the timeout happens, we do the contract cont. So that's the thing that allows us to ensure that things keep on happening. Now, if you look back at the contract data type, I've highlighted here some of the other components of Marlowe. We've talked about contracts, but there are also actions, which are things that impinge on the contract from outside. There are observations, and there are values. And let me just say a tiny bit about those. So actions can be one of three kinds. They can be a deposit. So we're waiting for a party to deposit a value into an account. So this is how money gets put into contracts. The contract waits for that action to happen. And as I said, we have to have timeouts on that, because if the party may not choose to perform that action. A party can be asked to make a choice from a range of values. And the ID of the contract contains the name of the choice and the person making it. So Alice makes a named choice from a range of potential values. And there can be a notification of an observation happening from off the chain. Now, observations are simply allow us to compare values using their relative size, using equality, and combining them using logic. And the values that we were allowed to look at include the money in an account, the current time in terms of slot number, choices made, values defined using let, and so on. So they're simple combinations of things about the current state of the contract, money in accounts, current time, and so on. So I think values reflect that they're simple data values. They're combined into observations, and then on the basis of whether an observation is true or not, the contract can evolve in different directions. And of course, included in those values are the choices made. So the direction of a contract can be and will be influenced by choices that participants make. And that really is it. It's this data type, contract data type, with observations and values as well. We specify the semantics. It runs on the, as I said, on the extended UTXO. You can see here in the diagram, I've tried to suggest that the yellow lines here indicate data flowing across transactions being spent, and doing that allows us to keep track of the current state of a contract, how far we've got through executing a contract. But again, it's this functional model that data flows through a network. So it is, perhaps I didn't stress this very much earlier on, but IOHK has taken this functional view of the world very seriously. It's using a functional language, Haskell, to do all the programming, but its model of a blockchain is functional. It doesn't have inherent state. And as I said, the Marlowe interpreter is a single Plutus program. I mean, it's just worth stressing here that when we do run a contract, we can put into users' wallets. This is something we're in the process of developing. We're not there yet, but it will be there in the final system, that we'll be able to automate actions so that if a deposit is required, we can automate, with the user's permission, automate that action in their wallet and generate transactions to go on the blockchain. So from a Marlowe contract, we can generate on-chain and off-chain components. And just to underline the point that inside the Marlowe, inside the Cardano world, what we have is this subset of Haskell called Plutus TX that compiles into Plutus core that runs on the blockchain itself. So we power things from Haskell. And just to be clear about what a transaction looks like, the transactions that get built are will contain a number of inputs potentially and a number of payments. So a single transaction may embody taking a variety of inputs and payments, and those steps of the contract are a number of steps of a contract are embodied in a single transaction that is placed on the chain. Okay, so I think that's enough about the generalities of Marlowe. What I want to do next is talk through some examples how we write real contracts using Marlowe, and then talk a bit about a financial standard that we've been working with.